So that covers measurements, data analysis, and these certain so-called interference corrections. That's what that general category is called. So let's now talk about calibrations, and this is where we introduce the transition from isotope ratios to actual age, and the uncertainties that come in here are what we would call systematic errors rather than random errors because they're not measurement related. So there are two basic sources or basic kinds of calibrations or categories. One has to do with the decay constants, the electron capture and beta decay constants. Both have some uncertainties, and that has to propagate into the age. And then uncertainties related to the ages of standards. And when I say ages of standards, I'm putting this in quotation marks because many people, when they talk about the argon-argon system and what calibration you're using, typically the focus is on what age of the standard did you use. But that's not really the real question, because the age of a standard, just like the age of an unknown sample, is dependent on the decay constants. So it's not really the ages of standards so much as the argon-40 to potassium-40 ratio of the standards. And I'm going to show you more what I mean by that. But that's because the age is also a function of the decay constant. So these, if you think of it in terms of the ages of standards, it's not really an independent issue. Okay, so first of all, the decay constants. Well, how are decay constants determined? Has anybody ever thought about that? Probably not. Right? You don't lose sleep at night thinking about this? Even I don't. But the most common way to determine the decay constants is to measure the nuclear activity, which is just the number of disintegrations of an atom per unit time. And this is, you use a Geiger counter or some kind of detector which can detect the decay event. And so this is the formula. So it's the nuclear activity is the disintegration rate, and then the atomic weight of potassium, the number of seconds per mean solar year if the nuclear activity data is in terms of disintegrations per second, which is typically the case. Those divided by the ratio of potassium-40 to total potassium, and that's because these measurements are typically done on all potassium, not purified, not just pure potassium-40. So the measurements that are made of the activity are made of natural potassium, which has just a little bit of 40 in it, plus a lot of potassium-39, and a little bit of potassium-41. That's why this ratio is important. And then Avogadro's number. So these are the values of some of these parameters. The number of seconds in a mean solar year is, I'm not sure what the uncertainty on that is, but it's definitely small enough to be negligible. And then this is the value of the isotopic composition of potassium, and this is the most recent value of Avogadro's number, although this actually changes every year. There's a very, very small change to this out in, this decimal place. So for our purposes, it's constant. So that's what where decay constants come from. And this is a plot of the measurements of the activity of the beta decay of potassium as a function of time, the year of publication. So what you can see here is that in the early 1970s, people stopped doing these experiments, amazingly. And what you can also see here is that it's not really the case that the most recent ones are the most precise. The most precise are basically done in the late 50s through mid 60s. And I must say, actually, a student of mine did a very thorough examination of this, and unfortunately, a lot of the uncertainties that are reported for these older data, you have no idea what those uncertainties really are. Are they one standard deviation? Sometimes they're reported as most probable error, which turns out to be the 50% confidence level. So actually, putting together this plot was a major literature search. So what I've shown here is the values that were used by Beckinsale and Gale in 1969. They published a recommendation for the decay constants based on this very small selection of all the available data. And this compilation was then formalized in an IUGS, International Union of Geological Sciences recommendation that was published in 1977, authored by Steiger and Jaeger. So there's this classic paper, Steiger and Jaeger, 1977, that has recommendations for a few of the decay constants for isotope systems that were being used back in the 1970s. There are a lot more in use now. But this was the basis for the decay constants that most people still use, actually. And you can see the subset of all of the data. And it doesn't even include some of the relatively precise ones for reasons that are not totally clear. But it was obviously a very, very subjective choice of which data to include. But in any case, whatever the rationale was, this is the summary compilation of these 1, 2, 3, 4, 5 measurements gives this value. So that value put into the equation I showed you earlier is what the widely used beta decay constant for potassium-40 is. And analogously, here are the data for the electron capture branch. And here you can see that they actually used only the most recent values. Oops. This measurement was made after this publication, so they can be excused for not including it. But they only included 4 of all these measurements, and this is the average value they got. So this 1.2% relative error propagates through that equation for the decay constant, and that's about how well we know the decay constant. It's about 1%. So that turns out to be a limiting factor in the ultimate calibration of the argon-argon or potassium-argon geochronometers. So to summarize, these are the values that were reported by Steiger and Jaeger for the electron capture and beta decay branches. And notice that there's no uncertainty given here. The Steiger and Jaeger classic report that everybody uses doesn't have any uncertainties in it. So none of the argon-argon or potassium-argon ages that were published until very recently included this very important source of systematic error, which is ridiculous. So if you try and compare a potassium-argon age or argon-argon age with a uranium-lead age, for example, you're not considering all the uncertainties, and you have to include these. It's really an amazing thing that for so long everybody just ignored these uncertainties. So as I mentioned, my student Min 12 years ago did a reanalysis of all the fundamental data and actually came up with the uncertainties, which are shown here. So the value that we get for the electron capture decay, which is the most important one for this chronometer, is pretty similar to what Steiger and Jaeger reported. The beta decay, however, we got a pretty significant difference for this. More recently, we have done a completely different kind of analysis, which I'm not going to go into very much detail about, although tomorrow I'm going to give a talk in which I'll go into much more detail about how we did this. But basically, we combined all of the activity data. So we included these results plus isotope measurements for the potassium 40 to argon 40 ratio for a certain standard, the Fish Canyon Sanidine standard. And then we included pairs of data from uranium-lead and argon-argon, where the argon-argon was based on the same standard, and with very careful criteria for comparison. We use only volcanic rocks, so there's no slow cooling effects or anything. So we use those uranium-lead dates also as a contribution to the decay constant. And in doing that, we come up with slightly different decay constants. As you can see, the difference between here and here and here and here, but much more precise values too. And this is very recent, and so the community is a little bit slow to change, but people are starting to use this calibration more and more. The general effects here are this calibration made ages a little bit older, about 1% older typically. And this calibration made things about another percent older. So from here to here is about 2% increase in the age of argon-argon ages, or potassium-argon. So increases ages that are based on this calibration, which I would say nowadays people have more or less switched to this calibration. So pre-2000 ages will increase by 2% if you use this calibration, but many ages published after 2000 only increase by 1% if you use this calibration. As a consumer or a researcher, if you're dealing with argon-argon data, it's very important to know which calibration was used and which standard was used. You absolutely must know these things if you want to compare these potassium-argon or argon-argon ages with anything else. If you are only trying to compare argon-argon ages with other argon-argon ages for example, to calculate sediment accumulation rates or volcanic extrusion rates or something like that, you don't need to worry about the absolute calibration because the differences will be the same. But if you're comparing potassium-argon or argon-argon ages with ages derived from any other system, you must know what calibration was used. And if you have any questions about how to compare or how to correct, ask somebody that knows what they're doing, because it's very easy to be confused. And I have to say, I apologize on the part of the argon-argon community that the situation has become extremely confusing. And if you don't really understand the details of what calibrations have been used, it can be really a disaster. And we recognized even before 2000 that there were problems with this calibration. And this was an IUGS convention, so it was an international convention. And so to change that, very difficult, because people don't like to change. But we could see very clear evidence that this was wrong. And for a long time, it was very hard to convince people to change. But as I said, most people changed to this calibration, but reluctantly. And then when we proposed another one, people really got unhappy. And so people ask me all the time, Paul, how many more changes do we have to have here? But the idea is, we want to be the most accurate. We want to be correct. And so conventions are good because it creates uniformity, but they can also suppress experimentation. And so you have to be willing to go against the convention sometimes if you want to improve. And this, I'm not trying to make a political statement here, but just a scientific one. So anyway, this is where we are now. This is slowly becoming adopted, and so this is I'm really trying to concentrate here just on the decay constants, but this value now touches upon the standard issue too, which I want to now address. So I've given you this form of the age equation. This is basically the generic argon-argon age equation, which uses this parameter J. And I've told you how we get J. And I've told you how we get these things. Now we can actually take the definition of J, which I gave you earlier, and substitute it back in here and see that here we only had to worry about the total decay constant of potassium 40. Now we've introduced this branching ratio, because that comes in when we substitute back in for J. Still has the argon 40, but now it's ratioed to potassium 40 of a standard. And this is the R value of the unknown relative to the standard, which, if you remember, I defined this earlier, is defined in this way. It's the radiogenic 40 to potassium-derived 39 ratio of the standard, of the unknown relative to the standard. So this is now a slightly expanded version of the standard age equation. And remember that this R value can be thought of as an intercalibration factor between a standard and an unknown, or you can also use it as calibration between two different standards. And what I mean by that is, whoa, wrong. So I'll explain what I mean by that last statement. So here's a summary of a few standards of various ages. These are kind of nominal ages. 1.2 million for this Alder Creek Sanidine, 28 million for this one. Here's two different values for this particular biotite standard. Here's a hornblende standard. Here's an even older standard, about 1 billion years old. And what I'm showing here are the R values as defined in the previous slide of these standards relative to the Fish Canyon Sanidine, which is also about 28 million, which is why this R value is close to 1. So if we want to, let's say, for example, run a sample using HB3GR as the standard, because it's a fairly old sample and you want to use a fairly old standard for the reasons I mentioned earlier, but you want to somehow relate that to the Fish Canyon Sanidine, which is extremely well calibrated, you can use the fact that the R value of the unknown relative to that of Fish Canyon is simply equal to the R value of the unknown relative to the HB3GR standard. This is what you measure, times the R value of our HB3GR relative to Fish Canyon, which is given right here. So this you can just get from the literature. And so you can effectively use one standard but relate it to another, relate it to a better characterized standard, if you see what I mean. So this just brings up a simple point that the R value of any one sample, standard or sample, relative to any other can be seen as a series of intermediate steps. So you can just multiply a series of these intercalibration factors together to get the R value of any sample relative to anything else. And for many of these, as I just noted, we have pretty well documented R values. And another point is that the R value of sample or standard Y relative to sample or standard X is just 1 over the R value of X relative to Y. So these are little symbolic logic facts that are useful for manipulating argon-argon data. Okay, whoops. So there's yet another form of the age equation, and this is just simple algebra. We can relate the age of an unknown to basically the same essential equation, except that now this is a function of the total decay constant times the age of some standard or some material whose age we know independently. So up until now, I've been talking about standards whose ages are derived from potassium-argon measurements. But now we can take any way that we know the age of a standard. It could be a uranium-lead age. It could be anything. History. We could take the eruption of Vesuvius and say we know exactly when that happened. We can measure. We know this age from Plinius Secundus, and we can measure this ratio of the unknown relative to a standard. Great. So as I say, tau is the age of a standard known independently, i.e. from uranium-lead astronomical calibration of the standard, et cetera, et cetera. So I want to focus now on astronomical calibration because this is a very active area right now. So using this equation, some years ago, a team of which I was a member, but it was led by Claudia Kuiper in the Free University of Amsterdam in the Netherlands, took a section of alkalic silicic tuffs in Morocco, but very near the former Spanish area of Melilla. So there are two little Spanish colonies, former colonies, in Morocco. I didn't know about this before I went there, but there was a nice series of these tuffs interbedded with sediments, and the sediments are very rhythmically layered, and the layers can be related to orbital variations of the Earth and the climate consequences of changing the orbit, basically the precession, the eccentricity, and the obliquity of Earth's orbit. So these variations in Earth's orbit affect climate, and these climate fluctuations are periodic. And if you can calculate Earth's orbit, which can be done back to about 50 million years now, very precisely, we can calculate, based on those three components of Earth's orbital periodicity, we can calculate the solar flux at a given latitude. And the solar flux, of course, determines climate, and the climate is reflected in the kinds of sediments that are deposited. And so here we have an alternation of these so-called sapropels, shown in black, and these lighter colored units, which are marls. So the sapropels represent cooler, wetter times, and the marls represent warmer, drier times. And if you can match this pattern to the calculated orbital variations or orbitally driven variations in climate, you can basically tell time, right? And this is a very active area of research. Mostly, I have to say, in Northern Europe is where most of this work is being done. Some in Italy, some in Spain, but the big center is in the Netherlands. And so using this approach, this astronomical tuning, so-called, each of these red dashed lines represents a volcanic tuff. And one can calculate the age based on this astronomical tuning model for each horizon in the section. And so what we did was to date these tuffs, a number of them, not all of them, in two laboratories, one in my lab and one in the Free University of Amsterdam. And you can see the results here. These are just summaries of literally thousands of analyses. And you can see, for the most part, we have pretty good agreement. So if you take the average of all of these ages which are all based on the Fish Canyon Sanidine Standard. If you take the R values that you get from that and use the age from the astronomical tuning model, you come up with an age of 28.201 plus or minus 0.023 million years for the Fish Canyon Sanidine Standard. So this is an approach that has been extremely popular. And in fact, from 2008, when this was published, until last year or so, this was the most common calibration age used for this Fish Canyon Sanidine. So this was very successful, but it has some limitations. First of all, you have to ask yourself, how reliable is this model? And surprisingly, this was accepted very, very quickly by most people who didn't question how reliable it was. But the main drawbacks to this approach are, suppose you have a climate event which is caused by a volcanic eruption, let's say, or the passage of a near-Earth asteroid or whatever, something that's not a function of Earth's orbital parameters. This would be a problem for this approach. Also, if you have disconformities where you have a period of non-deposition, sometimes these are easy to recognize stratigraphically, but not always. So the model relies on this being a one-to-one record of Earth's climate and with no missing time. And the problem is that the uncertainties that come along with those assumptions are impossible to quantify. There's an uncertainty associated with the astronomical calibration of this curve, which is supposed to be about 5,000 years. But that's just the mathematical uncertainty of the calculated orbit. It doesn't take into account the uncertainty in climate response, various other possibilities. So I was surprised to see how quickly this was adopted without much critical thought. But it was clearly a big improvement over what existed before. And I have to say that to use this approach, you have to use not only this independently known age here, but also the total decay constant. So the total decay constant that was used in this approach was the one I mentioned here, min et al., these values. So we can get a very precise age for this standard, but the question is now, in order to apply this age to calculate the age of a sample, the uncertainties in the decay constant are still a fact of life. You still have to deal with those. So the bottom line is that if you are using this astronomical calibration to date something which is close to the age of the Fish Canyon Sanidine, the decay constants don't introduce very much uncertainty. But if you're trying to date something that's hundreds of millions or billions of years old, the uncertainty in these decay constants becomes very significant. Okay, and I'm going to talk more about that tomorrow if anybody wants to see that lecture. So what we've done, I mentioned this even more recent calibration. We've taken the age equation and even generalized it further so that now we have three variables. That is the two decay constants and this ratio, which I call kappa. So this is now our age equation. And I already mentioned that this approach that we use, which I call the optimization approach, uses now the activity data for both branches of the decay and the argon-40 and radiogenic argon-40 and potassium-40 concentration data for this standard, and pairs of uranium-lead argon-argon data. And this approach yields an age of 28.294 plus or minus 0.036 million years for fish canyon sanity. Now, in this case, this age is not the main product of this calibration. It's a consequence of the calibration. You'll notice that compared with the previous one, so the age is pretty comparable, 28.294 versus 28.201, but the uncertainty shown here, 36,000 years, is 50% larger than the uncertainty derived from this process. So you might think this new calibration is a step backwards, but it's not, because the uncertainty that I just mentioned in the optimization calibration includes uncertainty in the decay constant, whereas this one doesn't. So what does this all mean? Here then is a summary of the comparison between this orbital tuning or astronomical tuning calibration and the optimization approach, the more recent one. So this stands for Renne et al. 2011, Kuiper et al. 2008. And what I'm showing here is the age as a function of the R value. So that's the R value of any sample relative to fish canyon sanity. And the width of these curves is a measure of the uncertainty, the error, if you like. I prefer to call it uncertainty. And you can see that these two calibrations result in very, very similar ages. In fact, even out here, this is roughly the age of the solar system, 4.5 billion years. The difference in age is something like 10 million years out of 4.5 billion. It's very, very small. So the two calibrations give very similar results, but the uncertainties are very different. This is the uncertainty of the astronomical calibration when you extrapolate that result, introducing the uncertainty from the decay constants. It's on the order of hundreds of millions of years by the time you get out here into meteorite land. Down here in the Cenozoic, the difference is pretty small. So that's sort of the comparison, and my suggestion to you and to everybody else is that this is really the preferred calibration. It's more precise, it's more accurate, and it could stand to be improved by the addition of more data, but the fundamental approach, I think, is quite workable. Okay, now one of the consequences of this new calibration is that, kind of ironically, considering that we use uranium-lead data as part of the calibration, is that now this new calibration of the argon-argon system is actually more precise than the uranium-lead system, which seems sort of difficult to understand, but it's true. And to illustrate that, here is a plot of age and uncertainty in age for various precisions of isotope ratio measurements. So these are the uncertainties in the R values, and the black lines for argon-argon, and in the gray lines are uncertainties in the uranium-238 to lead-206 ratio. So these are more or less equivalent measures of isotope measurement precision. So for infinitely precise isotope ratio measurement, there's actually some trade-off here, so that the argon-argon system is actually more precise up to about 1,500 million years, or 1.5 billion, and then the uranium-lead system becomes more precise after that. So that's for R, with the uncertainty of an R value being 0. And as soon as you start introducing uncertainty into the isotope ratio measurements, the argon-argon system becomes more precise, or actually in this case you would probably say more accurate, and that the difference, it becomes more significant with age. So this is why I say, ironically, the argon-argon system using this calibration is actually more accurate than the uranium-lead system, which helped to calibrate the argon-argon system. Counterintuitive, but true. And to be fair, most isotope ratio measurements nowadays, to be considered, state of the art, are in this area of precision. So the difference between the two is not as extreme, whereas if you get up into this area where the uncertainty is greater than 0.5%, that's not very good quality data, so it's not a really very good comparison. But this, when I show this plot to uranium-lead geochronologists, they get really mad. Okay, so the next section is going to be on different ways of combining argon-argon data, what I call age determination, but here I'm going to talk about isochrons, plateau ages, and some of the ways that data sets can be handled. Okay, so I'm basically going to talk about three fundamental ways of combining data to determine an argon-argon age. And the first one is what I call a model age, because it depends on the air correction. And this is simply, well, I'll come to it. The next one is the age spectrum method, which also depends on the air correction, although it has a little bit more information. And then finally, the isochron method, which does not require an air correction. So we'll start with simple model ages. So one of the nice things about the argon-argon method that I mentioned is that because we can measure all the information we need from just isotope analysis of a single sample, we can measure very, very small samples down to the size of single crystals. So single crystals of less than 1 millimeter, if they're sufficiently old and sufficiently potassium rich, are no problem. So if we simply melt a single crystal with a laser, then analyze the gas, calculate an age using the approaches that I've mentioned, we can derive a number of ages for single crystals from a single eruption, for example. And what we find very often, not always, but enough to be relevant, is that especially tephras of any kind, very often contain xenocrysts. And by analyzing single crystals one by one, we can recognize them immediately if they're sufficiently old that they can be distinguished. So here's an example from a tuff about 380,000 years old from Ethiopia, which has each of these analyses is a single crystal, and you can see immediately that we can very quickly recognize these two crystals as being significantly older. We can resolve them easily within the uncertainties, and they're very obviously xenocrysts. They were inherited from the wall rocks of the volcano, or they happen to be sitting around on the ground and included in the tephra deposit. We can also resolve a couple of crystals that are much closer to the age that most of this population represents. But if the uncertainties were much larger, we would not be able to resolve those. So this is an illustration of the fact that the ability to resolve complexity in a population really depends on the analytical precision that you can achieve. So here it's pretty straightforward and pretty clear. And I should mention that the way that this sort of probability diagram is constructed is to take each of these analyses and assume that the uncertainty in the age represented by these error bars is distributed in a normal Gaussian distribution. And so then we just take at a very fine increment, let's say every 10,000 years, we add up all the probability contribution from each of these Gaussian distributions and sum them up, and that's what generates this curve. So if you didn't have that probability distribution, it would be a little bit more difficult to recognize this mode from this more dominant mode. But this is really the essence of what these just single crystal age populations is all about. It's being able to resolve different modes, being able to recognize the effects of xenocrysts. And in some cases, you find results that are a little bit younger. And if they're resolvably younger, according to various statistical tests, you can infer that it might be due to alteration. That's the main cause for that. And that interpretation is often aided by the compositional information that we get from the argon-argon analysis, the calcium, potassium, and chlorine ratios. So very often, the effects of alteration on, let's say, plagioclase, very often it's a little bit of sericite, which is a very potassium-rich, like muscovite, and you will find anomalously high potassium to calcium ratios, and that helps facilitate this kind of interpretation. So that's pretty straightforward. The next age determination method that we often use is the age spectrum, and this is possible because we can heat samples not just by totally fusing them and analyzing all the gas that comes from a sample, but we can heat them in steps, and that's what the age spectrum is all about. So this plot shows the results of taking a sample. In this case, this is multiple crystals of plagioclase from a rhyodacite in Brazil, which is more or less at the end of the Paraná continental flood basalt province. And as we heat the sample incrementally, we analyze the gas that comes off after we heat it to, say, 300 degrees C, and then 350 degrees, and then 400, and so on. And the extent to which we can measure the same age within the error margins, which are shown by the vertical heights of these boxes, is an indication of how homogeneous the age in the sample is. So this gives rise to the concept of a plateau, which is shown by the fact that all of the steps from here to the completion of the experiment, where the sample was totally melted, all of these steps give the same age. So typically we plot age as a function of the cumulative amount of the argon-39 released. We could use argon-37 if we wanted to, but since 39 is related to argon-40, this is more acceptable usually. So the extent to which we have reproducible ages is an indication of how meaningful those ages are. The extent to which we have discordant ages, which is what you see in the first, say, almost 10% of the gas that was released, is an indication of some kind of disturbance of the system. And in this case, we see ages that are significantly younger climbing up to this plateau age, so-called, of 132.4 plus or minus 0.1 million years. Now, notice that this is another example of which this potassium-calcium ratio becomes very useful to interpret what this means. So a qualitative interpretation of what this information, this so-called age spectrum, is telling us is that the gas that's released at relatively low temperatures in these first steps is coming from the margins of crystals. And as we heat the sample progressively more and more, we're getting gas that comes more and more from the interiors of crystals. And this is not one-to-one, but it's generally, it's more or less true. And if we notice here that the potassium-calcium ratio is a little bit disturbed up here and a little bit elevated relative to the plateau, where it's very homogeneous, this is consistent with some sericitic alteration, which is responsible for these anomalously low ages. This is important because another way that this sort of age spectrum can be produced is if this plagioclase sample had been reheated. Suppose the lava flow, this is from a flow, was extruded, and then tens of millions of years later, a dike was intruded right next to it. And the dike introduces heat, which partially degasses argon from the plagioclase. That would produce a very similar shape of age spectrum. So having this compositional information, and also, frankly, petrography helps. I mean, if you look at this sample, you can see a little bit of sericite, mostly along the grain boundaries. So this is an example of how that's useful. So this age spectrum method is useful because it allows you to detect features like alteration. It also allows you to detect non-atmospheric compositions of the initial argon. And I'll elaborate more on that briefly. But if this age spectrum, which is calculated using an air correction, if this age spectrum, if this sample had non-atmospheric argon-36, or argon-40 for that matter, it would have to be homogeneously distributed in order to still yield this plateau, because the air correction would have to be uniformly incorrect in order to still yield a plateau. So a plateau is a good indication, but not perfect, that there is no non-atmospheric trapped argon-40, initial argon-40. So the age spectrum is useful for that purpose. It is also useful, as I mentioned, to indicate the possibility of partial degassing by reheating, the growth of secondary minerals, and so on. So the way that we derive an age from this age spectrum is to simply define a plateau in some way, and there are various ways of defining it. But generally, a plateau is defined as being at least 90% or 70% or something like that of the total argon-39 that's released. It has to be at least 3 steps, and no 2 steps anywhere in the plateau can differ by more than 2 standard deviations from each other. But there's no statistically rigorous definition of a plateau. So the definitions are kind of ad hoc, not statistically meaningful. And it's important to always define what the criteria are. In this case, I mean, there's no ambiguity about it. This is an excellent plateau. And the way that we actually combine these data to derive an age is just as we do with the single crystal results I just mentioned. We take the weighted average, where the weight factor is the inverse variance, so 1 over the standard deviation squared of each analysis. So the weighted average of the plateau steps is what we end up calculating as a plateau age. Now, one important subtlety, which I think many practitioners even don't appreciate, is that if you take all of the ages and the ages include the uncertainty that comes from the J value, because the J value has some uncertainty, which you have to propagate into the age. If you take the weighted average of individual step ages that include this uncertainty, you will tend to bias the result because the J-value uncertainty is systematic. Every single one of these steps has an uncertainty in the J-value. So what you actually have to do is calculate the weighted average of the argon 40 to argon 39 ratio, the weighted average of that, and then propagate in the J-value and the J-value uncertainty, if that makes sense. And for that same reason, plateau ages usually, when you plot an age spectrum, you don't include the uncertainties that come from the J-value because that's a systematic source of uncertainty. And you really, in order to define a plateau, you need to be comparing only the analytical errors, not the systematic errors. Okay, so that's the age spectrum. And now finally I want to mention isochrons in the context now of the argon 4039 system. So this is very much analogous to what I mentioned earlier with the potassium argon system. We can write the argon 40 as a function of the initial argon 40 in a sample times the radiogenic argon 40, which can be written this way. Divide through by a common isotope, again, as before, using argon 36. And now we're going to substitute in this definition of J into here for K40. And so this is what the isochron equation looks like. And so once again, this is the equation of a straight line with an intercept being the argon 4036 initial ratio and the slope being this combination parameter here. So again, this is what it looks like graphically. So if we plot argon 4036 versus 3936, so the intercept then gives us whatever the trapped ratio was, and very commonly when you plot argon-argon data in this way, this ratio will be 298, the error ratio. So it's a nice validation of that assumption. And here the slope is equal to this complex parameter, so you have to solve it for t, but it's approximately equal to this number here. So why do I emphasize this in the context of the argon-argon system compared to the potassium-argon system, where I said people really don't use it? First of all, it's much easier to take the results of a step heating experiment, which you can do completely automatedly. So you program a sample, and the next morning you have 50 analyses, and it's very, very straightforward to plot those kinds of data in this way. And you're typically measuring a very small sample where the hope, I won't say assumption, the hope that all of the individual analyses reflect a common initial ratio is much more likely to be valid. So the results of plotting isochrons from incremental heating data or step heating data are much more straightforward with the argon-argon system. And as I say, this is a very straightforward way to check whether the error correction is a valid correction and derive both an age and the initial argon ratio at the same time. The most common result is that the intercept for volcanic rocks in particular is atmospheric, as one more or less expects, because volcanic rocks more or less tend to be equilibrated with the atmosphere. For plutonic and metamorphic rocks, for various minerals within them, one finds atmospheric ratios or higher, typically. Lower than subatmospheric ratios are rare, and when they do occur, sometimes they're artifacts of various kinds, but they're very, very rare. And if you ever see an isochron in the literature that has a ratio of, say, 250 plus or minus 10 or something, you should go, extraño, and look at the results more carefully. So this is a very powerful tool, and it's very straightforward to generate this kind of information very quickly, and we use it all the time. There's another, I just wanted to show you, this was a hypothetical isochron. I'm going to show you now some real isochron data. So this is from a meteorite called Acapulco. I suppose it must have been found near Acapulco. And it's one of the very old achondrite meteorites, which I won't bother to define that, but you can see the age, 4507 million years. And you can see that the data in this kind of plot are very linear. And this is actually not where most of the data are. There's 33 analyses, so this is about a day's worth of incremental heating. And the next slide shows the detail of this little box. You can see a very nice collinear data set. Whoops. And remember, I told you that an MSWD value of 1 is what? Is that good or bad? How good? Fantastic. It's perfect. It's ideal. This is just luck. I mean, usually it would be 1.2 or 0.8 or something. But this is a great result. And what else do you notice about this? Is this sort of interesting? The initial intercept here, 40-36 ratio, is 0.1, plus or minus 4, so it's not that precise. But this is not terrestrial atmosphere. So if we made an air correction, a terrestrial air correction on the sample, it would have been a disaster. And this is a reflection of the fact that wherever this object formed, in the protoplanetary disk, there was no air, at least not like what we have on Earth. So this is very typical of extraterrestrial samples, is that we do find subatmospheric ratios. So this is the exception to the rule that I told you earlier. Okay, so there's another kind of isochron that can be used called an inverse isochron. And I'm not going to bore you with the mathematics, but it plots argon 36 over argon 40 on this axis and argon 39 over argon 40 on this axis. So here, this represents a mixing line between a trapped component and an intercept over here, which is pure age. So this shows the extent to which the trapped component is correlated with potassium, and at 0 potassium, this is where you are. So this is actually step heating data from Sanidine from Vesuvius, from the eruption that destroyed Pompeii. And you can see that the data form a well-defined line whose intercept over here corresponds to an age of 1,925 years, plus or minus 94 years. So that's about plus or minus 5%, which is a large relative uncertainty. But at this extreme age, that's doing pretty good. Now, I should mention that this was actually measured, let's see, 15 years ago. So we have to add 15 years to this age to be modern. You don't have to do that very often. But one of the things that's striking about this analysis is that the intercept over here, you see, is higher than atmosphere. So there's a trapped argon component in this Sanidine, which is not atmospheric. And it's very, very seldom that you can actually see this. And one of the reasons you can is, first of all, this is a large data set. And second, it's so young that you actually have analytical leverage on this. And so we can actually see this. It would not be possible to detect this, quite likely, in a sample that was 10 million years old or 100 million years old, because most of the data in this particular type of plot, which is called an inverse isochron, by the way, most of the data would be concentrated down here, and the precision with which you can calculate the intercept is much lower. So this was a little bit of a surprise because people are not really used to seeing excess argon, which is what this is called, in sanidine. And so to test this, we actually separated olivine from this flow and analyzed the olivine, not irradiated because olivine has no potassium, right? And we got this ratio, which is actually even lower than this one. Remember that this is 36 over 40. So being lower on this plot means even higher 40-36 ratio. So I forget what this translates to, but I think it's about 315 or so. So there very clearly was excess argon in this melt, and it was trapped in the sanidine and the olivine. We don't know how it was trapped. Was it trapped in melt inclusions? Is it actually argon atoms occupying defects in the sanidine lattice? We don't know. But other people have now found excess argon in sanidine in other examples, so it's not that surprising. So that's an example of the so-called inverse isochron. And this is actually has become more popular than the normal isochron. It gives exactly the same results mathematically, but it's graphically it's more it distributes the data in a way that's easier to visualize. So it's often preferred over the other one. And just finally to show you the relationship between an age spectrum and an inverse isochron. So this is an age spectrum that is just made up. It's not real. An age spectrum that corresponds to a very typical behavior which includes excess argon from, say, a whole rock sample or a ground mass sample of a lava flow. This kind of pattern is common, and the implication is that there's radiogenic argon derived from partial melting, say, of the crust or somewhere at depth related to the heat of the magma. And it gets trapped in different sites that have different retention of argon, some low temperature and some high temperature. So you get this so-called saddle-shaped spectrum. And this is more or less diagnostic of this excess argon pattern. In many cases, the minimum ages in the saddle come close to the true age, but not always. So this is a classic example of an age spectrum, which if you look at the same data in an isochron, can be completely resolved, completely understood. And again, this is just a hypothetical example, so of course it's going to work out perfectly. But this is what the inverse isochron looks like. And to show the relationship between the age spectrum and the inverse isochron, the ages in the age spectrum, again, are model ages. Those are based on making an atmospheric correction. So they are what you get if you take the atmospheric ratio on this inverse isochron axis and project it through each measurement point down to this axis. So this would be the age that you would get for step 1 in the age spectrum, step 2 over here, step 3, step 4, and then it comes back, step 5, and step 6, which is just exactly what I showed. So the point here is that the ages that you calculate using the model of atmospheric contamination gives you this wide variation in ages. But if you look at this as an isochron, it has an intercept here, which is excess argon. It's a perfect straight line, and the age is actually right there. So this is an example of how you can use an isochron to calculate an age that makes no assumptions about the composition of trapped argon and completely cuts through the issues that you have if you just use an age spectrum. And I think that's the last one. Yeah, okay, so after lunch we'll do this recoil problem and I'll show you some applications.